All right, we're starting chapter 1, which will be all about functions. And so today we'll just look at some of the basics of functions, starting with the definition. So a function has to assign a unique output to each input. You can't have multiple outputs for the same input. If you think about maybe personifying a function, I like to think about it like it can't change its mind. If today you input 5 and the function outputs 10, then tomorrow it has to do the same thing. If you input 5, it has to still output 10. It can't change its mind. It can't, today it outputs 10 for 5, and then tomorrow it outputs 20 for 5. That doesn't work. Even a week from now, I'd have to still give you the same thing. Input 5, output 10. And so if you looked at that on the graph visually, that means it has to pass the vertical line test, that any vertical line would have to only go through one point. We'll look at that in a second. All right, so let's play the Is It a Function game. Contestant number 1. Let's see here. So this one, we've got multiple x's associated with the same y. Is that okay for it to be a function? And the answer is yes. This one is a function. In fact, if we look at what we call a constant function, a horizontal line, every single x is associated with the same y. Every single input has the same output, but that's still okay. That is a function. fxn is my lazy/efficient abbreviation for function. So it doesn't matter if multiple x's have the same output, the same y. It's totally fine. What about contestant number 2? Now here we've got this one, we input 13 and it outputs 2. And then this one, we input 13 and it outputs 4. Well, if we've got the same x, multiple y's, that is not okay. This one is not a function. That's exactly what we're not allowed to do, have multiple outputs for the same input. All right, if we look at it graphically, that's where we can use the vertical line test. Well, all I need is just one vertical line that passes through multiple points, and that means no, it's not a function. This is a loser of the Is It a Function game. This vertical line represents an x value, and the 2 points represent multiple different y values for that same x value. All right, now this one, I can draw a vertical line that passes through just 1 point, but it's not enough to only draw one. What it has to be is that any vertical line you draw has to only go through 1 point. So really I would have to draw an infinite number of vertical lines, but I think that's enough to see that any vertical line I draw, only 1 point. So this one is a winner, winner, chicken dinner. This one is a function, wins the Is It a Function game. All right, how about from equations? Well, we're trying to see if we have a unique output, a unique y. So let's try to isolate y. Let's get y by itself. So if I add the x squared over, y equals x squared plus 1. Well, let's think. If I input any number, is there any way to get multiple outputs? And there's not. If you square a number, you can do that in your calculator, you only get one answer. Add 1, there's still the same, only one answer, one number. So this one's a winner. This one is a function. How about this one? Isolate the y, I'll add the x over. And then I'll square root both sides. So I'll have y equals square root of x plus 1. Then wait a minute, you should be thinking, did I forget something? Is there anything else here? If I square to both sides, if I add the square root, I have to add plus or minus. So what do we think now? If y is plus or minus square root of x plus 1, is it a function? No, that is not a function. Here, if I input a particular x, I'll get 2 possible y's, 2 possible outputs, either the positive or the negative. So that is not a function. All right, so now we'll go ahead and take a look at domain. So make sure we keep straight that domain goes with x, whereas range would go with y. So we're just going to look at domain right now. Range, we usually just kind of take a look at the graph and take a look at the possible y values. We don't usually do a whole lot with range. Domain is the one that we can do a little bit more without the graph, just algebraically looking at the equation. So we can do this without a calculator. Range, you would just need the graph of your calculator. And so there's two things that we're going to be looking for. There's two potential problems that we need to avoid for our functions, because there's two things we can't do. We can't divide by 0. Can't have the bottom of a fraction be 0. And now normally we say we can't square root negatives. The inside of the square root, what's called the radicand, can't be negative. It's normally what we say. We're going to try to be a little more positive. Let's be a little more glass half full instead of glass half empty. Let's think about what we can do. If we can't square root negatives, what can we square root? We can square root positives or 0. We can square root things that are greater than or equal to 0. Okay, so these are the two things to watch out for. So that means if you have something like number 1 here, it's just a nice simple polynomial, the domain's just going to be all real numbers. Or of course you could call that negative infinity to infinity. You can take any number in the world, raise it to the 5th power, multiply it by 3, subtract those, add 7. There's no number that you can't do those things for. There's no problems. Okay, so if neither of these things, a fraction or a root, are in the function, the domain should be all real numbers. Then we get to some more advanced things like logs or trig. But a nice simple polynomial, just going to be real numbers all the time for the domain. Now this one does have a potential problem. This one, we can't have 0 in that denominator. So the domain is all real numbers, everything except 0. And so something like this, we would have x squared minus 4 can't equal 0. So x squared can't equal 4. So x can't equal plus or minus 2. So we would say all real numbers, that's what the R with an extra line means, all real numbers, except for plus or minus 2. So that's one problem. Denominators can't equal 0. One thing to watch out for. The other is when we have these roots, these radicals, that's when we need the radicand, what's inside the square root, to be greater than or equal to 0. So we need x to be greater than or equal to 0. So the domain is all real numbers greater than or equal to 0. So those are kind of the simpler cases. Now is when it starts to get a little bit tricky, when we take a look at number 5. Let's put all these things together, make it a little bit more complicated. I'll start with the easier one. So x minus 2 can't equal 0. So now do make sure with something like this, when we give you both things, when it's a fraction and a root, do make sure that you address both of those problems. So I'll start with the simpler one. X minus 2 can't equal 0. So x can't equal 2. And then I also need to look at the root. I need to handle both of these problems, both of these issues in the same function. Okay. All right. Now it's just the radicand. It's just the inside of the square root that has to be greater than or equal to 0. It's not the whole function. It's not even the square root part, the actual square root. It's just what's inside square root. It's just the x squared minus 2x that I'm going to write greater than or equal to 0. There's no rule that functions have to be greater than or equal to 0. It's just what's inside the root. Okay. And then this right here, so I'm kind of onto a new thing here. This right here is just a problem from last chapter now. Again, I said these inequalities here that we solve with the critical point method, we're going to be critical. We're going to be really important. We're going to put them on every test. You're seeing them again here. You'll see them again in calculus. You really need to know how to solve these kinds of inequalities well. So we factor it. We need our critical points, the solutions to the related equation. And then we put those on a number line. So we've got 0, 2. It's greater than or equal to 0. So right now I can put closed circles. And then I'm going to test some numbers. Now, remember, when you test numbers, make sure that you do them in the factored form there. So I could do something like -10 there. Use this factored form to make your life easier, because then I can just say negative, negative, negative times negative is positive. because I'm just looking for, is it greater than 0 or less than 0? In here, I can put a 1, and so I'll have positive, negative, that's negative, and then over here, it'll be positive. All right, so I wanted it to be positive, so I'm looking for this section here and this section here. So I could just write out the answer for this right now, but let's try to combine it with this x not equal to 2. Let's see how that's going to change it. Well, I had a closed circle before because this said or equal to, but now if x can't equal 2, well, now I don't have a closed circle anymore there. Now I have an open circle. And so when I write my answer, it's going to be negative infinity to 0. 0 can have a bracket. It's got a closed circle. This inequality was or equal to. But for this 2 here, instead of having that closed circle, I can't equal 2. So I'm going to change it to a parenthesis. So we need to combine what we get from this inequality with what we get down here from looking at the denominator. And that is my domain. All right, so now why don't you guys go ahead and try these two problems here. Remember, the two things you're looking for is you can't have a denominator be 0, and anything that's inside a square root has to be greater than or equal to 0. Take a look at number 6 and number 7 there, and go ahead and give those a try. Right, so you can check your answers here. So for number 6, there's one thing that often gets missed. 0 is kind of like an orphan critical point there. It's not included in either of the intervals. It's greater than or equal to 0, so the critical points have to be closed circles. They have to be included in the solutions. And so that 0 we got to have as its own interval right there. All right. And then on number 7, this inequality was a pretty simple one here. And so I just solved it algebraically. I didn't do the whole critical point method. I didn't have to do all that. It was super simple. I just solved it kind of simply. And then you could just write your answer like this if you want to. If you want, you could put it all into interval notation, but this would be fine right there. And just notice, though, that this inequality here is only for the 5 minus x. If you did try to do a number line on number 7, you wouldn't do it with the whole function. It's only 5 minus x that you're looking to be positive or 0. All right, so that is the definition of functions and domain. Now let's take a look at a little bit more about functions. So we're going to take a look at when functions are increasing or decreasing, and we're going to take a look at maximums and minimums. And let's see, for some reason the graph didn't actually print on that. Let me try to bring it over from my other copy of the notes. I'm going to put that in there. All right, so with increasing or decreasing, what you want to make sure that you look at is that you're giving x values and you're looking from left to right are going to be the big things that people forget or get confused on. And so we'll take a look at this graph. If you look at it online, it should be in the notes there, but it just didn't print for some reason. And so you can see how I've kind of labeled this here. So the graph, we look at this and we often put these arrows at the end to show that it goes forever. So this end, you might look at it like it's going up. You might normally think about this side going up. For increasing and decreasing, we're going to say that this is actually a decreasing side. You can picture maybe an ant on the graph, maybe crawling around the graph here, and from left to right, the ant would have to crawl down. So it's crawling down, so it's decreasing. Then it switches to going uphill, so that's increasing, decreasing, and increasing there. And so when I write these intervals, what we're going to say is we're just going to give the x values for these sections here. So what we're looking at is, even though it's kind of, it's the y values that are getting smaller here. If you look at this, the fact that it's decreasing means that the y's are getting smaller. We're saying where it's increasing or decreasing, and where in math is usually an x value. So if this first section is decreasing, it's from negative infinity, so we're talking about the x's, down to -2. So negative infinity to -2. I'm actually going to use a bracket. I'll talk about that in a second. And then it switches to increasing from -2 to 1. Again, we're giving the x values of this section. And then decreasing from 1 to 5. And then increasing from 5 to infinity. And so we can actually use those brackets right there. If you wanted to, you could go ahead and do parentheses. You could say -2 to 1 and 5 to infinity. We're actually not picky on these, whether you use the bracket or the parenthesis. In AP Calculus, they let you use either. Just technically, you can use the bracket. That's why I show that. Otherwise, students get confused. It does seem like we're saying you're increasing and decreasing both at the same time at x equals 1. The issue is you actually don't increase or decrease at a single point. You increase or decrease over an interval. So like to the left of 1, everywhere to the left of 1 is smaller. So you increase all the way up to 1. You stop increasing at 1. The y value at 1 is bigger than all those other ones. And then same thing here. Because this y value is bigger than all of these over here, it decreases from this point all the way through the other ones. So they can be included. It's not a big deal. Don't worry too much about that. Just know you can use brackets or parentheses on those, unless there was an open circle on the graph. If there was an open circle, you'd have to use parentheses. So parentheses might be the safer answer. Right. And let's go back and look at domain and range. So domain is the x's, and range is the y's. And so for domain, you're going to look from the left to the right. Well, this one goes on forever in both directions. There's no gaps. So the domain is just all real numbers, or negative infinity to infinity. And then the range for the y's, you're going to look at the bottom of the graph up to the top. So we do have a bottom of the graph. The lowest y value is -6. So your range is going to start at -6 and then go up forever to infinity. So we're going to talk about maxes and mins. So there's something we call an absolute or global maximum, which if you looked at this function, well, it goes up forever. So you might say there is no maximum value. That's saying that the absolute or global max, there is none. There is no absolute overall biggest value. But there is something that we call the relative or the local maximum. You see one point that we might call that, it's this one right here. If you just look locally, if you just look relative to the points around it, that point right there is a maximum. And so we would say that the maximum is 4. If you wanted to, you could say at x equals 1, but the maximum value is the y value, that 4 right there. And so then if we said absolute or global min, well, the absolute overall, globally looking at the whole function minimum, is -6. And if you wanted to, you could say at x equals 5. But then relative, so that we would still include this one. We would still have the -6 at x equals 5. But then there's another point that we would consider a minimum, just relatively speaking, locally. And that's this point right here. If we just focused on the area around it, just that section of the graph, it's a minimum. So we would also say that this -3 at x equals -2 is a relative or a local minimum. And so if you're ever asked for any max or mins, they're talking about relative or local. All maxes and mins, that's the relative or the local. So why don't you guys go ahead and try these last three problems then, we'll just focus on the increasing or decreasing. Most of the rest of it's pretty straightforward. These are the ones that people can get a little mixed up on. Just remember, it's the x values you're looking at from left to right. And you can go ahead and use your calculator to see the graph for each of these functions and to find those intervals. Go ahead and give those three problems a try. So here are these answers here. I had to unfold my paper a little bit. And so I copied these graphs down. Again, I would just get these graphs from a calculator. Again, just make sure you use the x values. Like for number 1, you should have the 0 here, not the 1. And for number 2, you had to use calc_max and calc_min. Calc_max would find you that point. Calc_min would find you this point. And then number 3 is always increasing. It almost looks like it kind of levels off in the middle. If you zoom in a lot, it almost looks like a straight line, but it actually does keep increasing all the way through.